So many years ago, there was a funny TV show, reality TV show called What Not to Wear. And it would basically be these people, these fashion experts telling folks, usually men, what not to wear so they won't look so outdated and goofy. So just like with what not to wear, there's also when not to use Java streams, although sadly it's not quite as amusing as watching the What Not to Wear show. So we're going to talk about when not to use parallel streams. And knowing when not to do something is almost as important as knowing when to do it, because it'll save you from making the mistake of making your code parallel and then wasting time because nothing's sped up. Certain types of programs are just not suited for parallel streams. So we've seen this before. If the amount of time taken to split something is excessive, or the amount of splitting is done in a way that leads to uneven splits, then it's not really a win to use parallel processing. And the EX14 example that we talked about, where you can go watch the video that walks through that code, that demonstrates that issue in spades, because it compares and contrasts the performance of a linked list versus an array list to process and uppercase all the words in the works of Shakespeare. So we make ourselves an array list of the works of Shakespeare, and then we make ourselves a linked list of the words of Shakespeare, and then we run the performance, and you see that the linked list version is way slower as n gets big, because it doesn't split evenly, it doesn't split efficiently. And here's just some results detailing what you can find if you go watch the other video. When n is relatively low, there's not that much of a difference, but as n gets very large, then all of a sudden array list is way faster than linked list, because it splits so much better using the splitterators that come with array list, which are all constant time. Whereas for linked lists, they're linear time, and they copy data, and it's ugly and horrible. So again, array list splitterator runs in constant time, because you can compute the midpoint efficiently and split evenly. And so it's easy. There's no copying of any data, which is great. In contrast, the linked list version does all kinds of allocation of memory and then data copying, and it does it in ways that just don't split evenly or efficiently, so it's much slower. Another situation when parallel streams aren't going to give you a win is when the startup costs of parallelism overwhelm the amount of data you're working on. So again, coming back to the n times q model, if n is low and q is low, then you're not going to get much of a win. Here's an example, which you can see in my EX16 folder, where we're using parallel stream factorial computation and a sequential stream factorial computation. You can see the only difference is this one has a dot parallel flag in it. And when n is small, like n is 20 or whatever, there's really no difference. In fact, the sequential version is actually faster. It's when n gets really big, like n is, if you want to find the 100,000th factorial, which is a large number, as you might imagine, which is why we use a big integer, then parallel processing is a win. But when n is relatively small, the startup costs are not worth it. It doesn't give you any win at all. In fact, if you run the test, you'll see that for small values of n, the sequential solution is more efficient. Another situation under which parallel streams will not give you a win, which we've again talked about recently when we talked about collectors, is when combining partial results is costly. And you can go back and look at the EX14 source and the video that is describing that. And again, this is the complete works of Shakespeare, where we have something that's going to be stored in an array list. Let's just say we use an array list in this case. And if you use a parallel stream here with a non-concurrent collector, the performance doesn't work very well. It doesn't scale up very well, because you have to do all the merging of the subresults into these mutable result containers, multiple of them. Conversely, and another problem is we don't actually do much work here. If we have a lot of work, then the fact that combining is a little expensive won't be as big deal as if we have very little work. So if Q is large, then the fact that combining has overhead isn't such a big deal. However, the much better solution to do here is just to go with the concurrent hash set collector solution, which will only have a single mutable result container and no merging overhead at all. And again, as we just saw when we looked at the other example, you can see that when we have a relatively small number of elements, the differences are modest, but when you have a large number of elements, then the concurrent collector starts to really do a much better job than the non-concurrent collector. Another challenge is some stream operations don't sufficiently exploit parallel processing. So this example is my EX15 folder, and this is actually a really interesting example. We are computing two different streams that in parallel are figuring out the first n, figuring out the square root of the first n even numbers. So that's the requirement. We have to figure out the first n even numbers. And this version here that uses iterate and filter and limit is very slow when you parallelize it, because we have to make an ordered stream. We have to use these stateful operations like limit, which are not going to run independently. You have to keep track of where you are between the threads, which means that there's all kinds of synchronization overhead. And iterate just doesn't work very well. So iterate and limit don't work. They don't split well. They don't parallelize well. And if you run this example, you'll see this performance is kind of crappy for that version. In contrast, if we change the way we implement this, if we use the range method, which does in fact split nicely in parallel, and get rid of limit and get rid of iterate, this code will run blazingly fast, and it parallelizes extremely well. And that's because range splits nicely and therefore runs very efficiently in parallel. So two different ways of computing the same result. One parallelizes better than the other. So this, again, is what you need to learn if you want to use parallel streams effectively. And of course, another obvious situation where parallel streams will be of modest, if any, benefit at all is if there aren't many or any cores. Therefore, there's one core. If there's only one core, then you're not going to be able to get a speed up by using, or you won't get much of a speed up by using parallel streams, unless, as I mentioned before, you have some kind of I/O bound job with hardware that supports direct memory access, DMA, because then you can have things going in parallel even though there's only one thread at a time. So for older computers, not a big deal. But I mean, let's be honest, who's trying to write parallel programs for a Mac SE, right? Who's trying to write parallel programs for, BlackBerry or early Android phone or something like that? Nobody. So it's not a big deal. Another tricky thing about parallel processing with streams is there's no built-in way to stop the processing of the stream. If the stream, once a parallel stream starts to run, it'll run till it's done, or you have to manually instruct the various operations in the stream to shut themselves down. And this is what I call the Sorcerers' Apprentice problem, because it's often easier to start things up but harder to shut them down. And this is a common way of shutting them down, which is to define some kind of static volatile flag and then make sure you test that flag in the computations that are running in the parallel stream, and then shut themselves down, perhaps by throwing an exception or whatnot, if they're shut down. So just a bit more complicated to shut things down, but it's not impossible. You just have to spend more time thinking about it. And in fact, if you look at your driver program for the image crawler, there's a button that you can push that will tell the simulation to stop, or not simulation, tell the thing to stop running. If you start downloading your images and you're like, I'm going to go to lunch, cancel, that will shut it down. And it uses this technique. It sets a flag, and then it instructs the threads check that flag and shut themselves down. So that's the end of the overview of when not to use Java parallel streams. And so, as you can imagine, the wisdom of software experts and senior software developers and architects is to know these kinds of things. And if you aspire to those types of achievements, then it's good to know this stuff.